Hey everyone, welcome back to my channel where I guess I post my videos a bit intermittently, just depending on my mood and whenever I come up with a pretty good problem. But today I have a pretty special problem for you guys. So this is one of the problems coming from Harvard University's Department of Biostatistics qualifying exam. So this exam is an exam to assess if the students in the program are sufficiently prepared to remain in the program. And the exam has a theory portion and then an applied portion. So this is one of the theoretical problems and the problem I came up with for the exam. So there's a lot of verbiage on this page right here. So we'll go through everything slowly and then I'll present the solution to this. So suppose we're dealing with a random variable x with support on the natural numbers including 0. So this simply means that the random variable x is a discrete random variable distributed on the natural numbers. And for simplicity, henceforth, we'll call the first moment of x as a, the second moment as b, and the third moment as c. So the first question asks, we define the probability generating function, or PGF for short, as this function g of s equaling the expected value of s to the x power. So this s here is acting as the formal variable that we're taking, that is free to change as we take the expected value here. So the PGF is a pretty well-defined concept that's introduced in many first courses in probability. And I'll have a little review about this as well when we attack the problem. So the first question asks to show these four properties: that the function g evaluated at 1 equals 1, its derivative evaluated at 1 equals a, its second derivative evaluated at 1 equals b minus a, and its third derivative evaluated at 1 equals c minus b plus 2a. So if you haven't been introduced to probability generating functions, this might seem a bit foreign, but the actual manipulation of this expression is pretty cool. And if some of you are maybe familiar with combinatorics, the idea of generating functions might already be familiar. So the probability generating function works the same way in that it generates probabilities. The second question then is almost an extension of the first. Prove that the probability generating function satisfies this inequality. I missed a small portion in the statement here. So prove that for s in the interval 0, 1, this inequality is being satisfied. You can kind of see some relations between the first problem and the second problem in the sense that the coefficients in this expansion here are these computations of the derivative value at 1. So, The third problem then asks to prove that the probability that our random variable equals 0 satisfies this inequality. So negative 11/6 a plus b minus 1/6 c plus 1. So this seems to be a bit out of nowhere. But then going back to the idea that I mentioned that probability generating functions generate probabilities, well, somehow you would presumably use the second expression here to prove this. For the fourth problem here, we have that set these specific moments to be 1, 2, and 5. So the first, second, and third moments are respectively 1, 2, and 5. Then you can actually plug these numbers into this inequality in the previous expression to get that the bound on x equals 0 has probably greater than or equal to 1/3. Now I want to actually attain that bound. Give me a distribution on these natural numbers such that this bound is attained. This is actually a slightly more difficult problem than what the actual exam for the Harvard biostatistics students mentioned, because they were given a huge hint, which I'll present in the solution. In the fifth problem here, let these random variables x1 to x2 and so on be independent on the natural numbers, and they have the moments satisfying this relationship right here. So the moments of these random variables are not the same. Rather, they satisfy this expression here, but we are given that it's independent. I now want you to compute the probability that the random variables equaling 0 occurs infinitely often. This is actually, again, a slightly more difficult version of the problem presented in exam, which they were actually asked to prove that this probability right here equals 1. So you know what the answer is. So you try to get to that answer instead of actually trying to, find the answer in the first place. And then for the sixth subproblem of this part, suppose we're giving a Galton-Watson branching process. So again, unless you're taking some class in probability theory, you might have not talked about branching processes, so this problem might seem completely foreign. But in any case, on the exam given to the students, they're given this definition where basically you're starting out with one individual, and then each individual gives birth to more individuals, and then that individual gives birth to even more individuals as well. And these births are occurring independently and following some distribution. So we denote that birth distribution with this y of nk. And then the entire process of the total number of individuals per generation is then denoted by x. So we're given that the moments, these random variables that describe the births per individual are independent and identically distributed and have the moments 2, 5, and 13. The students were then asked to show that the probability of ultimate extinction, basically this process basically dips to 0 and then stays 0 forever, satisfies this inequality right here, square root of 33 minus 5 divided by 4. On the actual exam, the students were actually given to prove that it's greater than or equal to 1/6, which is actually a weaker inequality. But since we're not under a time constraint, we can actually go through the problem together and get a handle on this. And we can actually then deal with this even more dastardly expression right here. So pause the video if you want to give it a try, and then we'll jump to the solution. So in jumping to the solution, let me just copy everything here and drag it down because we'll be working with this later. We don't have to work with it right now. Nice. Cool. All right, so let's begin this problem right here. So for the first problem, if you aren't familiar with probability joining functions, we can try to write out some first few terms of this expression right here. So this g of s equals the expected value of s to the x power. So what does this mean? Well, when x equals 0, the probability of x equals 0, we have s to the 0th power. And with the standard convention that we're going to say 0 to the 0th power equals 1, this actually will always equal 1. Then when we add the probability that x equals 1, we get s to the first, and then so on. And then using summation notation, this could be more compactly written as probability that x equals k times s to the kth power. So the probability generating function, when you perform a series expansion of it, the coefficient of the monomial s to the kth power is the probability that the random variable actually equals that value. So that's what it is. So that's how it generates probabilities. But it doesn't just generate probabilities. You can actually get moments from this expression as well, specifically something called factorial moments, which is what this first problem here is getting at. So let me just erase this, and then let's attack the first problem. So we want to show that these expressions here are true. So g of 1 is what? So it's the same thing as expected value of our thing evaluated at 1. Well, anything to any 1 to any power equals 1, right? So this just simply equals the expected value of 1, which just equals 1. So that's satisfied. Then for the next one, the derivative of this expression, evaluated at 1. Well, that's just the same thing as derivative of s, expected value of s to the x. Now, we're going to have to assume some um, regularity properties to allow us to bring the derivative inside the integral. So basically, the expected value here is an integral, right? So assuming the proper regularity conditions, which I know to the mathematicians out there, you have to check these, but the point of these problems is that all these conditions would normally be satisfied. So we're going to kind of ignore them right now. We're going to interchange this. So sorry, guys, without having to go through this. We interchange these values over, then we perform that derivative. So the variable we're taking the derivative with is with respect to s. So the x is a thing that's being taken down with, and the power of derivatives of polynomials. We get x times s to the x minus 1, evaluated at 1, of course. Well, that's just simply just the expected value of x, right? Which just equals a. So that's also checked off as well. Cool. So you can see that we're going to keep on doing this for the remaining 2 subparts of these problems right here. And I'll leave it to you to see that the next part will be then the second derivative of g evaluated at 1 would then just give us expected value and then bring the second derivative inside twice. We get x times x minus 1 times s to the x minus 2, with the power of derivatives being acted upon again. And this is at s equals 1. Okay, so this is just expected value of x times x minus 1, which when we expand it out gives us expected value of x squared minus expected value of x by the linearity of the expected value operator. And this, by definition, just equals b minus a, which is exactly what we want. And then for the fourth and final portion of this problem, we just have to show that the third derivative at evaluated at 1 equals this. So again, I'll leave it to you to show that the work is pretty straightforward again, just to show that this is the same thing as x minus 1, x minus 2. And then when you need to expand this in terms of like the polynomial powers, and then perform the linearity expectation of each one, you get this expected value cubed minus 3 the expected value squared plus 2 the expected value. And plugging in the definitions of each one of these, c minus 3b plus 2a. And we are done with part A of this problem. Not so bad, right? So again, we see here that by plugging in 1, by taking successive derivatives and plugging in 1, we get something related to the moments of the distribution, not the probabilities. So it might seem initially that it's a misnomer that this is called probability generating function, but there's already something called a moment generating function that's reserved for something else. And there is a close relation between those that I can talk about in the future video. But for this problem, at least we're finished. So let me erase this right-hand side and let's move on to this part B of this problem. Great. So in part B of this problem, we now have to show that for all s in the interval 0 to 1 on a unit interval, this probability generating function satisfies this inequality. And it's going to seem very familiar because, again, the coefficients in each one of these inequalities look like the derivatives out here. and then divided by the corresponding factorial in a Taylor series expansion. So we might be thinking to use some application of Taylor's theorem to prove this. And again, the left-hand side of this problem statements I have here are actually more succinct versions of what's provided on the exam. On the exam, it actually said use Taylor's theorem to prove this. We're giving a lot of hints to the students to take to solve each one of these problems. So that should be the first step, right? Just by seeing that we have a bunch of derivatives given to us that look like the coefficients in a Taylor series expansion. Something should be screaming in your mind to use Taylor's theorem to prove this, and we're going to do that. So Taylor's theorem states that we have g of s, and then it equals g evaluate at some value. So the expansion we're going to be doing is going to be around 1 because we evaluate these values already at 1. So 1 plus, and then we'll keep on just writing some more values until we don't have any more of the expression to write anymore. And then that remainder term we'll write in terms of the remainder portion of Taylor's theorem. So then this becomes s minus 1 plus the second derivative evaluated at 1 divided by 2 factorial s minus 1 squared plus the third derivative at 1 divided by 3 factorial times s minus 1 cubed. And then, well, we don't have a fourth portion, so we probably want to stop that expansion right at that point. And it seems that, at least when I was grading the students' exam for this problem, people somewhat got confused the difference between Taylor's series and Taylor's theorem. The series itself is just keep on writing this forever. The theorem is then something that governs the remaining term. Specifically, it's kind of like a mean value theorem on the remaining term. So we have this to be the fourth derivative at some value t divided by 4 factorial s minus 1 to the fourth power, where this value t is in between s and 1, depending on how large the value of s is. But since we're given that s is in the interval 0 to 1, it's always going to be the smaller value. So this is going to be between going to be between s and 1. Which I want to just remark here that this is a subset of the interval 0 to 1. So this is by Taylor's theorem. That we can write out this kind of expansion. And then we made specific use that the remaining term looks like this. So when we plug everything inside, this will then equal basically what we have here plus the remainder term, right? So we have 1 plus a times s minus 1 for this portion right here and this portion right here, plus b minus a divided by 2 times s minus 1 squared plus c minus 3b plus 2a divided by 6 times s minus 1 cubed plus, and then that remaining term. So that g quadruple prime at t divided by 24 times s minus 1 to the fourth power. So now what we're left with trying to prove is basically suffices to prove that this quadruple prime of t times s minus 1 to the fourth power is greater than or equal to 0. Why? Because we know that this g of s equals exactly everything that looks like we're trying to prove in an inequality plus this remaining term. So if this term is non-negative, then this gives us our inequality right here. But this isn't so bad. You can actually show then, for example, that this quadruple prime of t times s minus 1 to the fourth power just equals the expected value of, by doing the derivative many times, x minus 1 times x minus 2 times x minus 3 times t to the um, x minus 1, 2, 3, 4 times, give me a little bit more room here, times that basically that s minus 1 to the fourth power. Oops, sorry. Okay. So, but clearly that's true. So, because if you evaluate each one of these expressions, this thing right here is greater than or equal to 0, because we are given that t is an element of s and 1, which is a subset of 0 and 1. This thing right here is also greater than or equal to 0 because it's something to the fourth power. And then this thing right here is also greater than or equal to 0. Why? Because x minus 1, x minus 2, x minus 3. So x is a natural number. So if it's a natural number that equals 0, 1, 2, or 3, well, then this entire expression equals 0. If it's 4 greater, then we're just multiplying a bunch of even positive numbers. So then taking the expected value will also result in something positive. So then we're done here. So we're done. Draw in the QED box, and that's it. Cool. So we'll keep on moving to part C right now. All right. So for part C, we want to prove that the probability of this discrete random variable equaling 0 satisfies this inequality. So like I mentioned, probability generating function generates probabilities. And then remember that in the beginning, I wrote that g of s equals p x equals 0 plus, and then all the other terms, which is k equals 1 to infinity, and then p of x equaling k times s to the kth power. So if I plug in s to equal 0, then all these terms in the summation is going to be annihilated because you have a bunch of things times 0. So that means that the only thing that remains is the probability that x equals 0, which means that the probability that x equals 0 can be given by simply evaluating your probability generating function at 0. Now, by part B, where we prove this inequality is true for all values between 0 and 1, and 0 is part of this interval, luckily just is on the other side of the interval, right? So we're able to actually get this inequality by doing a Taylor series expansion around 1, but it's true for any value between 0 and 1, and then we're going to take the antipodal, like the opposite point of this interval, to then give us this inequality, which I think is pretty cool, you know. So this is greater than or equal to, then simply 1 plus a times s minus 1 plus b minus a divided by 2 times s minus 1 squared plus c minus 3b plus 2a divided by 6 times s minus 1 cubed. And then I guess I'll bring this over so I have a little bit more room. Sorry, guys. So this is all at s equaling 0. So then we just have to simplify this. 1 plus a times -1 plus b minus a divided by 2 times 1 plus c minus 3b plus 2a divided by 6 times -1. And then I'll leave the algebra to you guys, but this does indeed equal the final expression we want to prove. Cool. That was relatively quick. It was meant to be quick as well. So, because then part C's, this seems to be the kind of dominating inequality to be used for the next two subparts, D. So let's move on to D now. So part D asks for A, B, C equaling 1, 2, and 5. When you plug it into this inequality right here, you get the probability that x equals 0 is greater than or equal to 1/3. Now show that this bound is attainable by actually constructing a distribution on the natural numbers to obtain that bound. So the students on the actual Harvard Biostatistics qualifying exam were giving a huge hint. So I'll give the hint right here as well, but then I'll also give intuition of why this hint makes a lot of sense. But since the students were under a time constraint and they were pretty much have to solve this problem and another problem within 2 hours, that we decided to make this problem a bit easier by giving a bunch of hints. But the hint they were given is that it suffices to assign probabilities for x greater than or equal to 5 to all just equal 0. So that seems like a huge hint, because then the students only have to concentrate on assigning probabilities for the values 0, 1, 2, 3, 4, right? Actually, no, the hint was actually even more stringent. It was actually greater than or equal to 4. All these probabilities can be assigned to equal 0. So you can definitely see that this hint is a huge hint, right? But why would someone actually even think about this hint? Well, so recall back to our proof of the inequality in part B, okay? So in the inequality in part B, so recall in part B to prove our result, we needed to prove that the fourth derivative of this intermediate value t divided by 24 times s minus 1 to the fourth power is greater than or equal to 0. Now, if this entire expression were to equal 0, then that means that our inequality is actually an equality, right? And then part B was used to prove this part C inequality. So if this were to actually equal 0 exactly, then the part B inequality would equal 0. Would equal exactly. And then our part C inequality would equal as well. So that's a huge hint to actually come up with that with the other hint that we can actually assign probabilities for integers 4 and larger to just be 0. So we might ask, when is this expression equal to 0? So let's think about that. Well, we could obviously choose s to equal 1, and that can give us 0. But the thing is, that's only a particular value of s. And then, of course, since in the part C inequality, we evaluated g of s at 0, this is obviously something that we can't further manipulate to give us exactly 0. So, well, this is obviously 0 if, for example, we actually have the fourth derivative of this t expression to equal 0. Or it's just the expected value of x times x minus 1 times x minus 2 times x minus 3 times t to the x minus 4 to equal 0. And again, this t is some intermediate value that lies between s and 1. We can't really control that because our choice of s affects this t here. But what we can do is we can make this 0 by choosing a random variable that only lies on the values 0, 1, 2, or 3, right? Because then no matter if the random variable is only distributed on those 4 things, then this entire thing just collapses to 0. So this equals 0 if our random variable just only has the support 0, 1, 2, and 3. So justifying the hint to set the probability that x greater than or equal to 4 just to all equal 0, and then concentrate on these probabilities right here. Pretty cool. Okay, so then let's actually do that. I'll clear up the board right here. So we just looked at the fact that we can set all the probabilities for this random variable that's 4 greater than or equal to 0, which obviously simplifies so many things in this problem, right? So we want to satisfy these moments right here, right? So let's do that. So let P of k to equal the probability that x equals the value k. Okay. So setting up all the moment conditions and probability conditions, we have 1 must equal probability of 0 plus probability of 1 plus probability of 2 plus probability of 3. And then the first moment is equal to 1, which is defined as 0 times p is 0, okay, that goes away. 1 times p of 1 plus 2 times p of 2 plus 3 times p of 3. Then the second moment is 2. So that gives us, again, p1 plus 4p2 plus 9p3. And then the third moment is 5. So then writing that out again, 27p3, right? So again, the way I came up with this system of equations right here is the fact that all these probabilities must sum up to 1, and then we're going along with the hint that the successive probabilities greater than that can be assigned to 0. The first moment just equals the sum of probabilities times the value of that. 0 times p of 0 equals 0, which is why I'm excluding that. 1 times p of 1 plus 2 times p of 2 plus 3 times p of 3. Then the second moment is just taking all these coefficients and squaring it. 1 squared is 1, 2 squared is 4, 3 squared is 9. And then the third moment would just be another multiplying we'll be cubing it. So 1 cubed, 2 cubed, 3 cubed. So we have the system of equations. And then something we have to modify here is the fact that we actually want this first moment right here for the probability equal to 0 to be 1/3, because that's what the problem says. Construct a distribution such that this bound of 1/3 is attained. So then this might be a bit scary because you actually have a system of 4 equations, but then 3 unknowns. So it might be possible you might not have a solution, and maybe the hint I mentioned earlier is actually not a hint in the right direction. But it turns out that one of these solutions is actually redundant in the end. I'll leave it to you to solve the system of equations, but in the end, what you actually get is P of 0, P of 1, P of 2, P of 3 to equal the solution 1/3, 1/2, 0, and 1/6. And then the rest of the p's, P of 6, I'm sorry, P of 4, P of 5, P of 6, and so on. This can just equal the 0 vector, right? So that's our distribution in the end. So it actually turns out that you only need 3 values to be non-zero. 1, 0, 1, and 3. So it turns out P of 2 also equals 0 as well. So that's the solution to this problem. All right, let's keep on moving. So the next problem now asks this question, and now this is getting to, more technical probability theory. That's not maybe the probability theory that you learn in high school, where you just simply count the number of events and do a bunch of things, right? So here is a little bit more specialized. So again, suppose we have a sequence of random variables which are independent, and then we have the sequence of moments right here. And then I want you to compute the probability that x of k equals 0 infinitely often. So when you hear the terminology infinitely often, it should bring up ideas of lim soup and everything like that. But it turns out this is actually a simple application of Borel-Cantelli. So we have, so this is E right here. By second Borel-Cantelli lemma. So if the actual sum of all these probabilities right here, not with the infinitely often inside of it, equals infinity, then the probability of this actual event happening infinitely often, which I would abbreviate as IO, equals 1. So there's also a first Borel-Cantelli where basically it's the converse of this, right? So if this were to be less than infinity, then the probability here equals 0. The reason why you can guess this direction, I mean, on the exam, students were asked to prove this equals 1, so this should actually bring up the idea of using the second one immediately because they see the 1 here, not the 0 in the first Borel-Cantelli. Another way you can actually kind of see this is because by the statement of the problem, we're given a lower bound. We're given a lower bound in part C for the probabilities that these equal 0. So if you're to actually use any of the results in that previous problem for this one, well, you then need to prove that some kind of lower bound still shoots off to infinity, and therefore this left-hand side must also shoot off to infinity as well. If you try to prove that this probability here, this probability here to equal 0 for that matter, well, then the inequality that you can use from the previous problem will be in the wrong direction. It wouldn't be strong enough to do what you're trying to prove. So that's kind of just a hint by the statement of the problem. So let's just do that. Okay, so we have that the summation that k equals 1 to infinity of the probability that xk equals 0, and then we can apply our nice inequality that we derived in part C. Okay, so we have negative 11 over 6, a of k plus b of k minus 1 over 6 c of k plus 1. And then when we plug in those actual values, we get negative 11 over 6, 2 minus 1 over k, plus 5 minus 2 over k, minus 1, 6, 14 minus 3 over k, plus 1. And when you simplify all this, you get 1/3. And sorry, this should be a greater than equal to sign. No, this is equal to, and this is greater than equal to. You get that this is equal to this 1/3 the summation of the harmonic series. I mean, well, 1/3 the harmonic series, which we know is divergent, so this equals infinity. And therefore, by the second Borel-Cantelli, this equals 1, so we're done with this problem as well. Whew. Great. Cool. All right. Let's now move on to part F and finish off this problem. But part F will be the most difficult part of this problem, so maybe it'll take a bit longer time than the other subparts. So let's look at part F. So again, the part F is the idea that we have a Galton-Walton branching process. And then you want to find the probability of ultimate extinction. Well, show that it's actually greater than or equal to square root 33 minus 5 divided by 4, which I'll just write here is approximately equal to 0.186, if we actually compute that. The students on the exam were actually chosen to prove a simpler result. So let's actually concentrate on the simpler result first. So a simpler result. Prove it's actually greater than or equal to 1/6, which is approximately equal to 0.166. So the bound is definitely improved, but it's not improved tremendously, right? So maybe for some purposes, this bound right here is sufficient. Now, the way that students were expected to solve this problem without having to do a bunch of additional math is to realize that, well, this probability of ultimate extinction is denoted in terms of a union that you see here. Okay, because why does union make sense? Well, we just basically want to know at which point, which happens some point in history, where this entire process equals 0. And because of how this is defined, once one of these sets happens, the successive sets that afterwards will also equal 0 as well. There'll just be a subset of this event. So we want to know if at any generation, this entire process equals 0. So that's why it is written in this union set notation. But clearly, the probability of a union is greater than or equal to the probability of any single event of that union. So specifically, let's say in the first generation, right? We just chopped off all the other union events, which again would contribute either a 0 probability or a positive probability. So clearly this first inequality is satisfied. But then if you think about what this means, well, in the first generation, this n equals 0. So that means this upper index right here just equals 1. So there's only one thing that's being summed over here, right? So that's the probability of this only one event here, right, equaling 0. But then we can actually apply the inequality at the last step, right? So we can just then say it's negative 11/6, the first moment, which is, I'm just copying from here, 2 plus 5 minus 1/6 13 plus 1. And then if you actually compute that out, this gives you 1/6, exactly what we want. But can we do better? Can we actually come up with this inequality that is actually square root 33 minus 5/4? And where the hell did that number come from, right? It turns out that this problem is obviously worked backwards to give us this bound right here, rather than this bound coming a little bit more naturally. So let's do this. All right. So there's a result from branching processes that states this: the probability of ultimate extinction, I'll just call it PUI. Okay, probability of ultimate extinction is the smallest possible root no, smallest positive root, sorry. Positive root of s equaling to gs. So in other words, it's the smallest positive fixed point of g of s. So for those of you who are still learning probability, haven't been introduced to this result, it seems a bit arbitrary. It's actually pretty amazing how this result is proven up. So go check out some other videos about this. But anyway, the students, if you want to solve this problem more formally, you would use this kind of result. The difficulty of this problem is the fact that we're only given the moments, and then we have an inequality given in part B that governs a lower bound for the generating function. So now a question that one might ask is, can I just simply replace this lower bound and then expect solving that, find the fixed point of that to give me a lower bound on the probability of ultimate extinction? It's not exactly clear that's true. So we have to work with some few steps to begin with, but that might obviously be a step in the right direction to try out, right? So let's do that. So let's define, let's say, this g tilde of s to be that lower bound. So to be that 1 plus a s minus 1 plus b minus a divided by 2 s minus 1 squared plus c minus 3b plus 2a over 6 s minus 1 cubed. Sorry, ran out of room right there. So let's define it like this, which we know is going to be less than equal to our genuine probability generating function. Okay, so when we plug in the values into this expression, what do we get? We get, I'm just looking at my solutions right here to write it out. We get that this is equal to 1 plus 2 times s minus 1 plus 3 halves times s minus 1 squared plus 1/3 times s minus 1 cubed. So then we want to solve this. Okay, so in order to solve this, we have to do this a little bit more meticulously. Okay, so something I want to notice is that we have g of s minus s. Okay, consider this expression right here. When we do this, we then get s minus 1. So I'll explain in 1 second where I got that, I guess. It's because, well, this expression right here is 2s minus 2 plus 1 will be 2s minus 1 minus s gives me s minus 1. Okay? And then this here I can factor out. I can factor out s minus 1 here, and then I have here 1 plus 3 halves s minus 1 plus 1/3 s minus 1 squared. Okay? And then I can then again factor out a 1/3 from the expression on the inside to give me 1/3 s minus 1 times 3 plus 9 over 2 s minus 1 plus s minus 1 squared. Only reason I'm just doing this is then the coefficient of the leading term, which would be s squared right here, is just 1. Now, this is a quadratic, so if you use a quadratic formula to factor this, because the roots here are certainly not rational, okay? So I'm going to skip the steps right here to then write out the roots to be in this form. You have, and then I'm going to rearrange everything so then like the order of the roots would be positive to negative to positive, right? So we have S1, S minus R1, S minus R2, which I'll define momentarily, and then S minus 1. So this S minus 1 here is brought over here. I just reordered this because the roots, because these R1s, R2s, R3s are defined as the following. R1 equals negative 33 minus 5 divided by 4. And this is all negative, right? So I want to mark this as less than 0. And this is going to be less than R2, which turns out to be square root of 33, ha ha ha, minus 5 over 4. So that's where this mysterious square root of 33 minus 5 over 4 comes from. And you can actually show that this value right here is also less than 1. Okay, so there's obviously a lot of work that was, clearly like done here, right? So we need to actually do this rather than saying solve g of s minus s equaling 0, because it would lead to 3 solutions. Writing it in this form clearly shows what those 3 solutions are: R1, R2, R3, and it's also written in the product that's actually in increasing order of the roots, right? And this is going to be important because we need to then argue that with this expression right here is befitting to allow us to argue that replacing our genuine probability generating function, find the fixed point of that with the pseudo version, which is a lower bound on it, and solving it actually still gives us a lower bound on the actual probabilities themselves. Okay, it's annoying. But the reason why this is interesting is because, well, clearly R2 right here is the smallest positive root, which we want, right? So we're almost there. So, but what does this expression tell us? Well, this expression tells us that if I were to make a little chart right here, that this thing is basically, if S were to be less than negative, if S were to be less than R1 right here, let me think about this for a moment. Yes, if S were to be less than R1 right here, then this entire thing would be negative. If S were to be less than R1. Why? Because then I have negative times negative times negative, which is negative. If S were to be between R1 and R2, then this expression would actually be positive. Why? Because we would have something greater than R1 times that, which would be positive. Positive, negative, negative. So that gives me something positive. And then again, if it were to be between R1 and 1, it would be negative again. So basically, because this is a degree 3 polynomial, you can clearly see that, like, by this kind of rule right here, we have, how g of s actually looks like. Well, we have R1 somewhere here, R2 somewhere here, and then 1 somewhere here, right? So we have negative, positive, negative, positive again. But most critically, I'm sorry, this is going to be g of s minus s and the tilde of s, right? But most critically, this portion right here is going to be greater than 0. right? So that's actually the information we need. So therefore, g of tilde of s minus s is greater than 0 for s in the interval 0 to r1. So, which is the same thing as saying that g of tilde of s is greater than s for s in the interval 0 to r1. So that's the thing we're trying to argue. Why? It's because, well, we know that g of s is greater than or equal to g tilde of s by our part B result, which then we show that is greater than s itself. So this inequality right here is true for any value of s between 0 and 1. And then this inequality right here is true for any value of s between 0 and r of 1. So that means that this is actually true for s in the interval 0 to r1. What does this mean? Well, that means that for the values of s between 0 and r1, g of s is strictly greater than s. So that means we can't possibly have a root for the solution of g of s equaling s on the interval 0 to r1. But you can also see that clearly, so therefore, I'll write this in words. Therefore, g of s equal s cannot have a root within 0 and r1. But since g of 1 just equals 1, so that's clearly a fixed point, there must exist a root for s within the interval r1 to I'm sorry, so listen, we have to make these open intervals because it actually equals 0 within at that exact value, right? There must exist a root on the interval r1 to 1. Therefore, probability of ultimate extinction is greater than or equal to r1, which we define to have been square root 33 minus 5 over 4, which is approximately, again, 0.186. Okay, this problem seems to have taken much longer than the rest of the problems as well. But yeah, this is obviously an interesting problem altogether, right? So some of my thoughts is just basically, it's an interesting idea that normally when we think about moments are derived from probabilities. But then given moments, can we then say something about the probabilities? And this probably is an interesting approach to that by using probability generating functions to derive these different bounds on these probabilistic events, given the moments of certain random variables that are involved in these events themselves. So I hope that you enjoyed this problem. So remember to like and subscribe and smash that subscribe button and everything, guys. So take care, and I'll see you guys on the next one.